Okay, so today we're going to be looking at relations and functions. A relation is just a relationship between input values and output values. So you put things into a little machine and you get an output value. All right, so then domain. Your domain is the set of all your x values in a relations, or your input values. When we write down domain, we usually use set notation like this and write our x values inside. Then the is the set of all your y values, which is all your output values. So after you plug the x values into your little machine that is your relation, the y values are what comes out of those. So that's just a little bit of vocabulary to show you what we are going to be dealing with today. Okay, so we're going to be looking at different representations of the exact same data. So you can see on my first set with the ordered pairs, I've got an x value and a y value. My second set of data is a table, but it's the exact same data. So -1 is my x, 2 is my y, and that's listed here in the table as well. It's just listed differently. And then if I were to graph that, -1, 2, very sloppily, would be there. Okay? So there's different ways to represent relations. You can represent them as ordered pairs. You can represent them as a table. You can represent them as a graph or as a mapping. A mapping is where you take the ordered pairs and put all your x's in one bubble and all your y's in a different bubble, and then you show how they are paired up. So for example, over here I have 0, 5. 0 is in my x bubble, and then I have 5 in my y bubble, and there's an arrow connecting the two showing that 0 relates to 5. And they're all paired up the exact same way, like that. Alright, we're going to be using mapping later. Okay, so for this example, it says to state the domain and range of the relation of the given ordered pairs. So remember, domain is the set of all your x values. So when I look at all these ordered pairs, all I have to do is take that first number in each set and list them in my domain. So that would be 2, -1, 0, 9, -6. So again, just taking these values, these x values, and listing them here. Okay, my range is the set of all my y values. So that would be -1, 4, 7, -6, and 5. So here, 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 and here. Those are all of my y values listed. Now, if any of these values ever repeat, you do not have to write them down a second time. Okay, so an example we did in class today was writing down all the names of the people at your table and then their respective birthdays, and then we wrote down the names and the birthdays as a mapping. So, for example, let's say at my table there was Ayton, Cunningham, Croto, and we'll call that good. And then my birthday is in March. Cunningham's birthday, I don't know, is, when would Cunningham's birthday be? July. We're making this up. And then let's say Croto's birthday is also in July. Okay, so a mapping would be, oh goodness, why did I write that down a second time? You only have to write it down once. Silly me. So then we would have Cunningham showing an arrow to July and Croto having an arrow to July. So that's just kind of an example of a mapping that we did in class today. All right, domain and range of our relation. So for that example that I just did, the domain would be all the different teachers that I listed. So Ayton, Cunningham, and Croto. The range would be the months. So my birthday's in March, and we're pretending that Seaham and Croto both have the same birthday month, which is July. Now, since they're both in July, I only have to write it down once. So that would be our domain and range of our example today. All right, now looking at whether or not a relation is a function. A function is a special relation. It's where each input value only has one output value. So the way I think of this is the Minnie Mouse Bowmaker game that my daughter has on my iPad. So the Minnie Mouse has this silly machine that's called a Bowmaker. And you take this ribbon, look at my art skills, Mr. Ramirez would be so proud. Take this ribbon, it's got polka dots on it, and you plug that into your machine. Now, the only thing in this Bowmaker that I can get out of that is a bow, and this is where my artistic skills go downhill. Is a bow that has polka dots on it, just like the ribbon that I put in. I'm not going to put in a ribbon with red polka dots and get out of my machine a bow with purple stripes. It doesn't make sense. A function is a relationship where you put something into a machine and you can only get one possible thing out. All right, so on this next example, it says, is the relation a function? Why or why not? Ooh, let's hope we get through these notes okay. So, is this a function? What we need to check is to see if each input value only has one y. -4 goes to 1. -7 also goes to 1, but each x value has only one y. -4 is not going to 1 and -2. I had a pen. -4 is only going to 1, and 7 is only going to 1. So yes, this is a function. And the reason why is because each x only has one y. Now when we look at example 2, you can see that 5 is paired up with 4, but 5 is also paired up with 1. This is not a function. This would be like taking purple ribbon into Minnie Mouse's Bowmaker and getting out a bow that is purple and red. Can't happen. All right. So that is how you tell if a relation is a function when you're given a mapping. When you are given a graph, though, we do a different kind of test. It's the same thing, it just looks different because our data is represented in a different way. We've got a graph. The vertical line test says that a relation is a function if and only if it intersects the graph at just one point. So you can see on my first example, the graph is only touching my red vertical line at one point. On my second example, though, if I were to lay a vertical line across there, it is touching my graph at 2 points, here and here, which means this x value, whatever this is paired up with a y here and a y here. So this is not a function. All right, so a little bit of vocabulary. Functions can be described in two variables, x and y. The input value, or the x, is known as the independent quantity, and the output value is also known as the dependent, which means y depends on x. All right, so a good way to remember this, that's a lot of vocabulary, and it's all very synonymous. X, input, dependent, so on and so forth. So I'm going to give you just an acronym for remembering this, which is the very notorious Texas couple, Dixie and Roy D. It's actually not a real couple, we just make them up. But it's an acronym to help you remember what goes with what. D for Dixie is the dependent value. I is input. X is the X value. And then the second I is independent. No, that's not right. Dependent, input. What am I missing here? Input is X, is known as the independent. Okay, so independent, input. Oh, domain. That's what I messed up on. Okay, so the D actually stands for domain. There we go. I had to look at Roy's name to figure that out because Roy, the R stands for range, which matches up with D and domain. Okay, so in Roy's name, the R stands for range, the O is the output, the Y is the Y value, and then D is the dependent value. So all of these things go together. You've got Dixie and Roy D. Roy D is all the Y values and all the synonyms. Dixie is all the X values and all of X's synonyms. Okay, so functions can be described in two variables. We just went over that. An ordered pair, X and Y, is a solution if you can plug it in and it gets a true statement. Okay, now the graph, an equation of two variables, y equals mx plus b, represents all the ordered pairs that are solutions to the equations. What we're going to do on this example, it says, is 2, 1 a solution to y equals 3x minus 5? What that means is if I plug in 2 for x and 1 for y, does that make the equation a true statement? So I'm going to plug in 1 for y and then 2 for x. So y equals 3 times x, which is 2, and then minus 5. So 1 equals 6 minus 5. So 1 indeed equals 1. So this is a solution to my equation. 2, 1 is a solution to y equals 3x minus 5. Now, anytime you're graphing equations in two variables, there's an easy way to do this, and it works for linear equations and it works for nonlinear equations. What we're going to do is we're going to construct a table of values, and I'm going to start off by picking out values for x. These could be any values that I want. I want to try to make it easy on myself, so I picked some very simple numbers. Now what I'm going to do is I'm going to substitute those in to my function and get the y values. So that would be y equals negative, my first x value that I'm going to look at is negative 2 plus 6. That would be y equals positive 2 plus 6, which is 8. So I'll put that over there. Now I'm going to substitute in my second x value, which is negative 1. So y equals negative 1 plus 6. So y equals positive 1 plus 6, which would give me 7. And then I can plug in the other values. So y equals negative 0 plus 6, which would be 6. And then y equals negative positive 1 plus 6. So y equals 5. By this point, I'm hoping you're guessing that the next value is going to be 4. Negative positive 2 plus 6. Yes, x, y equals 4. There was a pattern to that. Okay, so now I can graph that. 1, 2, 3, 4, 6, 7, 8. Negative 2, 8 is way up here. Then negative 1, 7 is here. 0, 6 here. And then 1, 5 is there. And then 2, 4 is there. Okay. And those should make a straight line, but I'm having to graph this rather inaccurately. Okay, so that works whether you're dealing with a linear equation or a circular equation. You can always plug in x and y values to graph. All right, now the next thing is to tell whether or not a function is linear. So anytime you're looking at an equation, if it can be written like this, y equals mx plus b, where the exponent on our x is 1, that is a linear equation. Now, there's another way to name this equation. Instead of saying y equals, we can say f of x equals. That f and then parentheses x is read like this. To sound intelligent in math, the way you say this is f of x, which means the function value or the y value at a certain x value. So in other words, f of x is y. All right, on the next two examples, it says, tell whether the function is linear. In other words, it can be written like y equals mx plus b. And then evaluate the function where x equals negative 3. Okay, when I look at the function for a, I should see that because the x has an exponent of 2, this is not linear. Because lines never have an exponent greater than 1. That's going to make a parabola, not a line. Okay, so this is not linear. That's part of my answer. Then we're going to plug in negative 3. So I'm going to write this in function notation. F of negative 3 is negative, and then negative 3 squared plus 5x plus, oops, I wrote 5x. That should be 5 times negative 3. Plus 10. Whew. All right. Let's get this up a little bit. All right, so negative 3 squared is positive 9, but I've got to take the negative of that. So that's negative 9. 5 times negative 3 is negative 15, and then plus 10. Negative 9 minus 15 is negative 24, plus 10 would be negative 14. So the function of our equation where x is negative 3 is negative 14. Okay, now example B, we have g of x, which is just a way of saying this is a function, it's just different than the f of x that we had, equals negative 3x plus 4. My first question is it linear or not linear? This is linear because it can be written in the form y equals mx plus b. The next thing is to find the value of the function where x equals negative 3, which means I'm just going to substitute in negative 3 for x. So g of negative 3 equals 9 plus 4, which would be positive 13. Okay, so we talked about whether your group names and birthday data would be a function. My birthday data with the teachers would be a function. Each x, there's only one teacher named Ayton. There's only one teacher named Cunningham. There's only one teacher named Croto. So it is a function. Then what if I switched it and had the birthday months be my x and my teacher names be my y's? That would not be a function because Croto or July would be linked to Croto and Cunningham. So Does not work. Okay, so then we are moving on to slope. We've been talking about linear functions a little bit. When we talk about linear functions, we like to look at how quickly those lines are changing. So we're looking at the slope of a line, which is the ratio of its rise, vertical change, to its run. So when you're given 2 points, like x1, y1, and good grief, and x2, y2, you can find the rate of change by subtracting your y values over your x values. Okay, so good formula. I do not have a handout for this notes, so you will want to write down the title at least, and then if you think you might have a hard time remembering that pattern or that formula, you might want to write that down also. Okay, example 1 says find the slope of the line that passes through those 2 points. So I'm just going to take -2 minus 4 all over 7 minus 5. So -2 minus 4 is -6. 7 minus 5 is 2. So -6 divided by 2 is -3, which is my slope. That means it is rising, which in this case, since it's negative, it's actually falling at a faster rate than it's running. So it's a little steep. All right, example 2, find the slope of those 2 points on that line. So it would be -2 minus a -7, should be plus positive, over 3 minus 4. -2 plus 7 is 5. 3 minus 4 is -1. So to simplify that, that would be -5. Now, so this slope is steeper than that one. This one is falling at a faster rate than this one is. So at Schlitterbahn, I would personally much rather ride this one than this one because I like the faster rides. My son, who's a scaredy cat, would like to go on that one. He doesn't like the fast rides. Okay, so classifications of slopes of lines. Whenever you have a positive slope, you are going to be going from the bottom to the top as you look at it from left to right. Negative slope decreases as you look at it from left to right. A zero slope does not rise at all. It only runs. So you have 0x plus b. A vertical line, that's when your equation looks like this. X equals some number because you have an undefined slope, and this one is not a function. Okay, so I'm going to give you some little pointers to help you remember the difference between a zero slope and an undefined slope. When you do your subtraction with your y2 minus y1 over x2 minus x1, and you get something where you have 0 divided by some number. If you look at that, that looks like the word on. Okay, that means it's on like Donkey Kong, and that's when you have a zero slope. Okay, now when you have a number on top divided by 0, you cannot take any number and divide it by 0. It doesn't work. That's when you have an undefined number, so that is no, undefined. Now, a little trick to try to help you remember when it's a vertical line versus when it's a horizontal line. If you think of it this way. All right, undefined slope, remember the alphabet. In the alphabet, it goes U and then V. So when you have an undefined slope, that's when you have a vertical line. Sometimes we struggle with remembering which way it goes. When it's undefined, is that a horizontal or a vertical line? Or zero slope, is that horizontal or vertical? If you just remember UV, undefined slope, meaning the zeros on the bottom, that's when you have a vertical line. All right, so we're going to find the slopes of these lines. Now, I'm going to go through this pretty quickly just because I'm about to run out of battery. So, hang with me. 7 minus 2 over negative 5 minus a negative 5. That would be 5 over 0. That is an undefined slope. That's a no-no. All right, example 2 would be 7 minus 7 over 5 minus 3, which would be 0 over 2. So we have 0 over a number that's on like Donkey Kong. That's when it's a 0 slope. So it would be a horizontal line. All right, example 3 would be negative 6 minus negative 2, which would be plus positive, over negative 1 minus 4, which would be negative 4 over negative 5, which, oops, gotta erase that. So that would be a positive 4/5, because both of the negatives would become positive. All right, and then the top one, negative 2 minus a negative 2, that would be plus positive, all over negative 2 minus 3, 0 over negative 5, 0 over a number, that's when you have a 0 slope. Okay, so we did this example on the whiteboards, finding the slope between these two lines, because it's good practice to work with fractions. So it's 5/2 minus 1/2 over 5/3 minus 1/3. Okay, 5/2 minus 1/2, I have a common denominator, so I can go ahead and subtract those numbers. That's 4 over 2. Over on the bottom, that would be 4 over 3. All right, now I can simplify the top. 4 divided by 2 is 2. But on the bottom fraction, I can't simplify 4/3 any. Now, I could plug this in the calculator, or I could just try to figure out how to deal with fractions. So, let me show you how to deal with these fractions. This is the same thing on the numerator as being 2 over 1. We have a complex fraction. To get rid of the denominator, we're going to multiply the top and the bottom of this fraction by 3/4, the reciprocal of 4/3. So this would be like multiplying 2 times 3 over 1 times 4. So that's going to give me 6 over 4. And then everything on the bottom cancels out, which is why I did that. 6 over 4 can be reduced down to 3 over 2. Okay, so that was my slope. Not too bad. All right, which line is steeper? Line 1, 4, negative 1, and 6, negative 4, or line 2, negative 4, 5, and negative 2, 7. So we just have to find the slope of line 1, which would be negative 4 minus a negative 1 over 6 minus 4. That's plus positive, which would be negative 3 over 2. Line 2, the slope is 7 minus 5 over negative 2 minus a negative 4. That would be 2, excuse me, over 2, which is just 1. 3 over 2, if you think about it in these terms, is like 1.5. So the one that is a steeper line is line 1, because it has a steeper slope. Okay, so the next was we just answer this question in our journals using complete sentences. Describe the difference between a discrete function, which is what we looked at here, or what this is, first one on the left is an example of discrete function. The example on the right is a continuous function. They are both functions, but one's called discrete, one's called continuous. So I want you to look at those pictures and then try to give me a few observations about the differences between discrete and continuous functions. All right, and I don't have the assignment here at home with me, so you will want to come see me to get the assignment out of the workbook for this assignment. All right, we are all done.